But sometimes in some Hamiltonians, exact analytical expression is available for wave function, the spectrum, and then when we want to modify MPS in order that it gives exact analytical results when it's available. Well, the most famous spin model is XXX Heisenberg. So let me remind. Hamiltonian, M is the number of lattice side, M capital is the length of the lattice. And this is 3 Pauli matrices in one lattice side, 3 Pauli matrices in another lattice side. It was introduced by Heisenberg himself in 1929. And then eigenfunction was found by Hans Bethe in 1932, a long time ago. So the other model which I will be talking about, very soon after it was introduced, it was generalized. We can add magnetic field to here. I think notation is magnetic field summation, magnetic field summation all sigma z m. And then also very soon anisotropic formulation came up, XXZ, which I will be also talking about. Just need to adjust notation for the beginning. So my notation will be like this: summation lattice side, sigma x, Pauli matrices, m plus 1 plus sigma y, plus delta. Delta I will denote. I'll just change notation for this delta soon. Sigma z m plus 1 minus 1. We can also add magnetic field along Z-man magnetic field along z direction. The relation of this model is like this. When delta equal to 1, this is XXX, but it's ferromagnetic XXX, meaning the ground state is a product state, it's ferromagnetic state. When delta equal to minus 1, then this XXZ maps back to here with a plus sign. With anti-ferromagnetic one can actually, I will consider the case of even length of the lattice. M capital, total length of the lattice is even number. Then I can introduce unitary transformation, which is product of sigma z in even lattice size. To M and M run from in here. So every other side. And this unitary transformation actually will change this to minus signs into plus, and with delta equal to 1, we map back to here. Further notations, delta, this anisotropy parameter, which plays very important role. I will denote by cosine trigonometric function of 2 eta, and this angle eta will appear in many formulas later. So eigenfunctions of the Hamiltonian, the way Hans Bethe wrote it this way. So in order to write them down, I will need some notations, like for example, sine function. The epsilon will be sine function, which is equal to plus 1 or minus 1, depending on if m is greater than 0 or m is smaller than 0. So this sine function will appear. All kind of anti-symmetrization will be made. So eigenfunction of the Hamiltonian. So I'm just trying to diagonalize Hamiltonian, or Hans Bethe diagonalize it. N energy N. So this eigenfunction of the Hamiltonian look like this. N will be different number. I'm not confusing. The M is the length of the lattice. N will be number of spin down. So in all the formulas will be 2 different integer numbers. Mn, I guess. So the eigenfunction constructed like this. I'm starting from product state. This is ferromagnetic state where all spins looking up in each and every lattice side. Then I flip the spin down. Sigma minus the spin lowering operator in some lattice side. Lattice side number M1, M2, M3, Mn. And then I'm taking some linear combination of these states and sum up with respect to the positions where the spins flipped down. So chi is the many-body wave function, which is the central piece of this Bethe Ansatz. And then it looks like this. Well, kappa. Depends on a lot of stuff, but let me write it down. The Q is permutation, so I will be permuting momenta of the particles. Well, the point of view, this was like empty state, ferromagnetic state. I flipped one spin down. This is like creation of the spin wave. Spin wave somewhat similar to the particle, so sometimes I will I will be talking about spinons or magnons, sometimes they call them particles. So Q is a permutation, it will be permuting momenta of the particles. So summation will consist n factorial terms, because I sum up with this n factorial terms, so that many terms here. Parity of the permutation, then plane waves, product of the plane waves. Here I sum up with respect to all the particles, overturned spins. M is coordinate, like x position of the spin down. P is momenta. Well, momenta we shall later parameterize with something else, with some spectral parameter or rapidity. So that's the lambda, which will be clarified soon. And there is pairwise interaction. There is a double product here. Multiplied by product. And here I have so that's the general structure of Bethe Ansatz. I will specify notations in a moment. But the general idea, first of all, there is a lot of terms, n factorial terms. So computationally, it's not efficient the way it's written. This piece is, I'll say, one-body reducible, because without double product, looks like free particles, free fermions, actually. This is actual interaction. When two particles collide, they go through one another, they pick extra phase. This is actually actual interaction. And then also show that the model is actually interacting, it's not free. So let me write this parameterization. If I just use momenta, then scattering matrix will be a complicated function of this momenta. It will depend on the difference and the sum of momenta. So in order to simplify the expression for the scattering phase, I will parameterize momenta with some rapidity, so spectral parameters. Momenta will look complicated, but the scattering phase will depend only on the difference of this momenta. That's the reason of the interaction of extra parameter. So in the XXZ case, this momenta, which appears in here in the plane wave, I will parameterize, the traditional parameterization in the literature log. CH is the cosine hyperbolic. I have to write it down, so I just show the notations. Eta, lambda is my spectral parameter, which will play a role, will parameterize momenta, and eta is related to the coupling constant, to anisotropy. So this is my momentum in the case of XXZ, and scattering phase, which depends, then scattering phase depends on the difference of these lambdas, and it looks like this, sine hyperbolic. So eta is anisotropy, you still remember eta. Sine hyperbolic. All right, so this is, and then the total energy is equal to the sum of energies of individual spin waves, epsilon of lambda alpha. And then this individual energy of one individual spin wave look like this. Eta, 2 eta, and here I have my spectral parameter or rapidity, different people call it differently, and also magnetic field. Zeeman magnetic field. Also, often people impose periodic boundary conditions on this model, at least traditionally in statistical mechanics. And those periodic boundary conditions look like this. M is the total length of the lattice. P is this momentum parameterized by spectral parameter. And here I have this product of, with respect to beta. And this is a pairwise scattering of particle alpha on other particles. Spin waves. So this is pretty much exact diagonalization by Bethe of this XXZ. This is actually a complete set of all states. And well, maybe this is for XXZ. XXX looks very, very similar. XXX is just anisotropic, this first one which Heisenberg introduced. I just, for XXX, I have to change parameterization. P will be I log I squared of -1, lambda spectral parameter. This is under log. And then theta will be I log I plus lambda, I minus lambda, and epsilon energy of one individual spin wave will be -2 square of the spectral parameter plus quarter plus magnetic field. Otherwise, I just plug this expression into here and I get solution for either one. So anyway, this was a solution by Bethe. I mean, solution, the complete set of all eigenfunctions of the Hamiltonian. And it looks actually computation non-efficient because I have so much terms here and factorial terms. If I put it in the computer, it probably will crash immediately. So our idea was like this. First of all, when we look into this, we first forget about interaction. Look into the free part. This looks like Fourier transform, but Fourier transform, we know that we can do this, we can calculate it computationally efficient, fast Fourier transform, like quantum Fourier transform is centerpiece of Shor algorithm. He managed to write it down as a product of n factors and everything become computationally efficient and nice. So the idea, maybe we can write this thing, this horrible sum, as a product of n factors. It's kind of yes, but we need the tensor networks for this, and that's, I'm going to explain how to do this. So eventually we shall rewrite this wave function psi n in the following form. I will be explaining notation. We shall introduce some creation operators, spin lowering operators, creation operator of the eigenstate of the Hamiltonian, and there will be several of them. I mean, I have several lambdas here, like many momenta, each momenta corresponds to lambda. So, and by the way, this is not one equation, this is system of equation, and here alpha should be 1, 2, 3, 4 to n. So eventually we'll be able to write this eigenfunction as the product of n factor. Each B creation operator will depend on its own momenta or spectral parameter, and we apply these operators, and operators will be MPO to this ferromagnetic state, which is product state. These operators, which I will eventually construct, they're kind of nice because they commute with one another. It will become clear out of the construction. This helps. And also, eventually, the tensor network, which calculates this thing, will look like this. Well, let me draw some picture. Maybe large square. So actually, this is all lambda 1s. All lambda 1s. And then this will be representation of this B operator. Then the next B operator, which will have all lambda 2s inside. Lambda 2 connection. Lambda 2. Then also lambda 2, and so on. Each line corresponds to one of the B operators, and the last one, I'll have like dots, dot, dots. The last one will be made out of lambda n, all lambda n's. So this will be simple network, and I'll be explaining what all of this means eventually, step by step. So this is like a block. I mean, everything made out of this block, and I will call it L operator. And let me specify. So what I will be trying to do right now, I will try to reproduce this wave function for the XXX case. So I'll be guessing this L, but I have some pretty good guidance how I guess. I'll explain as it goes on. So this first elementary block in this tensor network.
I'm confused about M and N. So
M and
so
N.
N, capital N has to be 2 to the M, right? Because, I mean, it could
Capital
goes
M,
from-
no, capital M actually have to be even number, but this is number of the lattice set. The total dimension of the Hilbert space is 2 raised in power M.
2 to the M, yes.
But M, due to some technical reasons, well, remember I multiplied everything along the even lattice side. So, I mean, in order to be, for the lattice to be bipartite, it has to be even length. So M, that.
And so in the tensor network,
In the tensor network, this ladder is different because I start M with the product state all spin looking up. And then some of them I flip down. That's N capital, which is smaller than M capital. Those are 2 different integer numbers. And kind of should not be confused.
but what does it represent? So it represents
It represents this wave function. This wave function. See, the wave function is like scattering phase of N particles, N spin waves, and N magnons. And then this tensor network represents this wave function, which was written by Hans Bethe in 1932, so last millennium.
I see, so that's a different representation.
Yeah. Which, I mean, supposed to be computationally efficient because I'm following ideas of Peter Shor. Like instead of horrible sum and factorial terms, I want a product of N commuting terms. So I expect this will be better, computationally more efficient. Anyway, so I'm trying to build this tensor network. So first of all, this square, like elementary thing. This is like really simple thing. This will be linear function spectral parameter for the XXX case. So I'm just guessing this. And I'm telling you the result of the guess. So this elementary block out of which the whole tensor network built. Of course, this is physical indices, quantum indices, and this is auxiliary ancillary indices, like standard normal auxiliary. I will use the word auxiliary. I have to combine 2 languages of tensor network and algebraic Bethe Ansatz. So sometimes I will use double terminology. So this elementary block called L operator, I mean in Bethe Ansatz. And this L operator, that's a notation, ML. So M, this L operator corresponds to one physical site. This is site number 1 of the lattice of the physical. I mean, in here, I have these ordered spins, right? This I have in mind like ordered lattice, site number 1, some number 3, and so on. So in the beginning, they were ordered. So each of this vertical corresponds to one lattice site, another, third, and this is like physical actual appearance. So this is L operator, physical indices in site number N, and dependent spectral parameter should depend on spectral parameter. I know that my wave function should oscillate depending on the momenta. So look like this, lambda, linear function of spectral parameter, and then I write minus. Square root of -1, and here. So those sigma m are quantum spins. They act non-trivially in the quantum direction. And this is auxiliary space, so this is horizontal. This is L operator. And then I'm going to build the whole tensor network for the wave function out of this. So maybe I just also write L operator for the, so this is XXX case. XXX isotropic case, like more primordial. And XXZ case, I'll write it differently. For XXZ case, L operator, the elementary block, I will write this as explicit matrix in auxiliary space. An explicit matrix in auxiliary space look like this. Cosine hyperbolic function, lambda spectral parameter, anisotropy, sigma zm quantum spin, and here eta anisotropy, and here I'll have eta anisotropy, cosine hyperbolic, spectral parameter, anisotropy, quantum spin. Well, in principle, I can also write this as explicit matrices 2 by 2, then it will look similar. So, just, as I said, different languages, right? So, this operator, they satisfy some remarkable equation, which is called the Yang-Baxter equation. So, let me write it down and then explain mathematical and physical meaning of this Yang-Baxter. Yang-Baxter equation at the very center of this solvability solvable models. So what this means, here I have the same latest set. So quantum operators, this one, are the same here. But 1, 2 means that I have two different copies of auxiliary spaces, like here and here. So this is tensor product of two auxiliary spaces, like roughly speaking, four-dimensional space. So these are matrix. X is kind of in tensor product of 2C2, both of them auxiliary. And then I have explicit expression for this R. I'll write them in somewhat different form. So both XXX and XYZ, both XXX and XXZ will fit in the same notations. As I said, this Bethe Ansatz wave function, the physical meaning can be compared to free models. In free model, I can say that dynamics is one-body reducible. If you just diagonalize Hamiltonian in one-body sector, I'll figure out, well, all quantum numbers, then nothing else happens in many-body sector. I just multiply one-body wave function, anti-symmetrize them, and that's it. Bethe Ansatz is not free because two particles, when they collide, there's a scattering matrix which depends on the momenta. But the whole dynamic of Bethe Ansatz is two-body reducible. So two-body reducibility is the central property of this Bethe Ansatz solvable model. Are matrix which enter into here. So it acts in tensor product of two-dimensional spaces. So I can write this as four-dimensional matrix. Just some specific notation for the matrix element. This is F, this is G, and then this is F again. This is 1. And this F and G are just functions, normal functions. They're different in the XXX and XXZ case. XXX case, mu F mu lambda 1 number, square root of -1 mu minus lambda, and G is just this piece. G mu lambda is I mu minus lambda. So this was XXX case. In the XXZ case, which is Q deformation, this is, I have to use this sign hyperbolic function. All right, so by now we have all the notations. So this elementary block, which I'm trying to sell you for the tensor network, is L operator which satisfies this equation. This is Yang-Baxter equation. This is mathematical representation of the idea of two-body reducibility. I can rewrite this. Sometimes people write this like this: 1, 2, 3 equal to 1, 2, 3. And this exactly mathematically means the many-body scattering matrix is tensor product, is product of two-body scattering. Okay, anyway, nice. What I do next? So I'm telling you that for elementary block, I have chosen this L operator which has this nice commutation relation. But this relation is really beautiful because it withstands something which is called co-multiplication. So what's this co-multiplication? So I'm still trying to explain notations in my tensor network. So next thing I do, I will introduce monodromy matrix. Monodromy matrix is this piece. So I just take several L operators, multiply them into auxiliary space. And this is important, evidently, for understanding of my tensor network. So this one line, this lambda, quantum sticking around, lambda, same lambda. So I multiply operators in the auxiliary space by quantum indices. This is tensor product in the quantum space. So there is some specific notation. Sometimes people denote this by T. This is traditional notation of Bethe Ansatz. And sooner or later, I will need to write this as explicit matrix in the auxiliary space. In the auxiliary space, this is actually matrix 2 by 2. So I can write like A, B, C, D, and A, B, C, D are quantum operators in all of the spaces. So sooner or later, so what's good about this relation, then it will stand this co-multiplication. In other words, T satisfies the same commutation relation like L. Let me write them down. That's a central property. Sometimes some people call it from local to global. Anyway, so my T, I can write another mathematical formula. So T equivalent to this, I can write L in the first lattice side, lambda multiplied by the second lattice side, and so on, and then last lattice side. And then these things satisfy the same relation like L operator. The same R matrix, exactly the same, still 4 by 4. Then here I have T lambda T mu, T mu, T lambda R lambda mu. I can put this indices. So this is first auxiliary space, second, first auxiliary space, second, and this is 1, 2, 1, 2. Our matrix is exactly the same. See, this is like remarkable theorem that everything works because of this co-multiplication. So starting from here, if this is valid for each and every L operator in here, then I can prove that. I skip the proof because, given ideas. All right, so this is important. There is several consequences out of this, immediate consequences. First of all, in principle, I can divide by this. I mean, multiply by R inverse from the right-hand side. And then if I do that, R T lambda T mu R inverse T mu T lambda, I can take trace of this in the 4-dimensional space, in the whole tensor product of two auxiliary spaces. Then this thing will cancel, right? And I'll get something. In order to write it down, I need some notation. Tau of lambda is trace of this T of lambda in the auxiliary space. So this means that this is A of lambda plus D of lambda. And if I take trace of this in 4-dimensional space, tensor product of two auxiliary spaces, I will immediately obtain that these things commute with one another. Tau of lambda is a scalar in auxiliary space, but this is quantum operator. Actually, it will be closely related to Hamiltonian. And then this tau of lambda commutes with itself at different values of spectral parameter. I mean, if I take trace, this will cancel, but here I have lambda mu, here I have mu lambda, right? So it will be trace multiplied by trace, but in a different order. So this is commutation. There is also some extra nice piece because this R matrix has some special properties, some special value when lambda minus mu is equal to I, it turns into the slope gate, into permutation. And this is really helpful in order to write a local Hamiltonian. I can actually, well, let me write it down first and then comment later. So XXX, we're talking about XXX. The Hamiltonian I wrote down, remember Heisenberg 29. So if I take logarithmic derivative of this trace of Mondrian as special value of spectral parameter, then I can reproduce the original Hamiltonian, XXX, the one which is 1929 of Heisenberg. So this is nice, because I can take a logarithmic derivative here. Then, I'll get that my Hamiltonian, I mean Heisenberg Hamiltonian, XXX, commute with T of lambda in any value of lambda. This is infinitely many conservation laws. So somewhat similar to Professor Vidal lecture. If you want, I can write some of them. It doesn't look like yours, but I mean, if there will be some, I can write some of them if it's interests anybody. Do you want me to write them? Okay, but they don't look like yours.
Okay.
Okay, so conservation laws by now, I
They're not local, right?
they're not local, they look like Hamiltonians. So Hamiltonian describes the direction of two nearest neighbors. The next non-trivial conservation law describes interaction of three nearest neighbors, and then 4, 5, and so on. Each of them are local. We call them local because it's a sum of the local density, one multiple sum of the local density. So it's not local like sigma z, but you have to sum up some local expressions. Well, I call Hamiltonian local because it's sum up of local expression. Do you want me to write down conservation law? Okay. Anybody develop it? One is like super nice, you know. I hope you say that. I was trying to provoke you. So, epsilon, ABCD. This is anti-symmetric tensor, right? So the first non-trivial conservation law, which comes with Hamiltonian. So look like this: summation. And here I have three nearest neighbors, like sigma, 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 A, B, C, M, M plus 1, M plus 2, and then, let me erase this, epsilon, A, B, C. So I take three Pauli matrices and three neighbor anti-symmetrization, like a volume sum up. So this one can prove it comes with a Hamiltonian. You want me to write all of them fastly, all of them, the rest? Okay. In order to do that, we need this boost operator. The rest of them we need to obtain recursively. I mean, like I know Hamiltonian, then I know the next one, and then if I know n of them, how I get the next one. And it's done by means of boost operator. Yeah, I hope you remember this. So boost operator looks like this. Boost operator is like Hamiltonian, some similarity to Hamiltonian for XXX case. Sigma, sigma, m, m plus 1 multiplied by m. And then the conservation laws constructed like this. The conservation law number L plus 1 is equal to commutator of conservation law number L with the boost operator. So for example, this one is a commutator of the Hamiltonian with a boost. This one. I can calculate, you know, blah, blah, blah. But if I calculate commutator of this with the boost, I get the next one and the next one, and actually all of them, as you say, complete set.
But they have more and more terms?
Yeah. So this is 3, next will 4, we'll have 4 interactions and so on, till the full length of the lattice. Okay, anyway, we're just trying to write the wave function, factorize the wave function, Bethe Ansatz wave function. Our matrix, I hope you remember, but by now we actually want to write these commutation relations more explicitly. Remember, I told you that I can derive this commutation relation, right? R lambda mu. So this is very explicit matrix 4 by 4, and T is, you know, like one line of this tensor network, which I wrote as explicit matrix 2 by 2 in the auxiliary space. So now I want to understand better the commutation relation of these matrix elements of this T, A, B, C, D, between themselves. So let me write some of them, some of these commutation relations. I have to write something. Okay, first of all, B commutes with itself. I mean, out of here, I take, this is equality of two matrices 4 by 4, from my point of view. So I can just multiply row by the column, I get 16 scalar equalities. So let me write a table. Some of them are useful, some less useful. So let me write 3 of them, the ones which I will use. Number one, which everybody likes, is B operator, which later will be creation of spin wave. Creation operator commutes with itself at different values of momenta. The other one looks like this. A operator, it has conservation laws, and B is creation, right? And for D, similar. I mean, A plus D, trace of Mondrian matrix, depends. I mean, it commutes with Hamiltonian. So I will try to diagonalize all of them simultaneously. I will try to find eigenfunctions of T of lambda, which is A. This is A of lambda plus D of lambda. I can diagonalize all of them simultaneously. They commute with one another. And Hamiltonian also commute. And I expect that eigenvectors will not depend on lambda. I mean, at the end of the day, they commute. So eigenvectors should depend on something, but not on this lambda. And that will come out eventually. So, okay, so D operator. I mean, A plus D has a Hamiltonian, so that's the thing which I want to diagonalize. Here I have F. F is some scalar function element entry of R matrix. Okay, so this is really, really useful commutation relations, but they're good. But I need something else. I need highest weight vector. Remember, I'm applying my MPO to some vector, to this ferromagnetic state, which is product state. So I need to know how the entries of this T and individual L operators apply to this ferromagnetic state. I mean, in the end here, I have this ferromagnetic state, right? I apply all of this. So just pure commutation relation is not good enough. I need to know L operator I erase, of course. So L operator of XXZ. So I want to apply this L operator to the state with spin up in his lattice side. And this L operator looks like this with some cosine. Here I have like sigma z, another cosine sigma z, something here, and here I have sigma plus m multiplied by something. So I apply this to ferromagnetic state, sigma plus x, and confirm this will vanish, right? And this vector is eigenvector for sigma z, right? So it will turn triangular. L operator after applying turn triangular. So what will happen with this L operator? Let me write it down. So after I apply this to the spin up state, I get the following: cosine lambda minus I eta. I had sigma z here, but it turned into 1 after application here. 0. Here I have some non-trivial operator, m sine 2 eta, and here I have cosine lambda plus I eta. Sigma z also disappeared because I applied this. Okay, nice, triangular matrix. But I mean, in order to get my monodromy matrix, I had it somewhere. So my monodromy matrix was a product of L operators, like L1, lambda, L2, lambda in the auxiliary space, and Lm lambda. Well, triangular matrices is, if you multiply two triangular matrices, you get also triangular matrix. It's a group, right? So that's nice. So this means that in principle, I can calculate the application of my ABCD operators to the ferromagnetic state. Well, at least C is equal to 0 because it's lower triangular element. So what comes out by now, I can take the whole T operator, which is product of L operator, which is this whole thing, which is kind of non-trivial, and then apply this to fully ferromagnetic state, these product states in each and every lattice side. It will turn, remember, we're writing this as an explicit matrix in the auxiliary space, it will become triangular, some complex valued function. This is, I'm just looking, oh, B, I'm sure it's B. And so, meaning what? That C operator, well, tensor network, well, maybe you remember this. Okay, so now I'm sure that I will have to draw it again, but I still need space. So what we got out of here, the C operator, annihilation operator, kills this ferromagnetic product state, so this is highest weight vector. And these eigenfunctions I can calculate. For example, xxx, a xxx of lambda will be equal to lambda minus I divided by 2, raising the power total length of the lattice. D will be complex conjugated, raising the power. And then for xxz, I also have some expressions. So by now, I am prepared to prove that I constructed eigenfunction of the Hamiltonian. So with all of this, I want to show or to prove that this construction starts for ferromagnetic state, which is product state. Then I apply my B operators. B of lambda n, B of lambda n minus 1, blah, 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 B of lambda 1. So let me some notation, say n. What I can do by now, I can sum up my two operators, A plus D. I mean, they commute with Hamiltonian, and they contain all the conservation laws. And if I diagonalize them, then I will know eigenvectors of the Hamiltonian. I want to apply to here. Well, I'm equipped because I want to move A through the product of B. I can use this commutation relation. This is kind of nice term. A go through, give some factor. Second term creates some trouble and some terms which I don't really want. Here is similar. The first term, this is some kind of a factor. When B goes through D, just some factor. This is troublemaker. We have to cancel contribution of this. If I just apply this, and then eventually, if I use this, A and D will hit this ferromagnetic state and will turn into one of those functions, A and D. So, in principle, if I calculate this carefully, kill the contribution of unwanted term, I'll get the eigenfunction. So, the result of this calculation looks like this. Theta is depends on everything. So it's a number, it's complex valued function, not an operator. Depends on all lambda, and on mu it's not an operator, that's a number. And the same psi n. So I managed to construct eigenfunction. But this lambda has to satisfy some equation to kill the contribution of unwanted terms. And this extra equation in the abstract form, they look like lambda j. This is eigenvalues of these diagonal operators. N k from 1 n f ratio of 2 f's, lambda j, lambda k, lambda g equal to 1. So this is condition of cancellation of these unwanted terms which appear from here. I can write this more explicitly. In the end of the day, I know f explicitly and all of this a, b, c, d. So if I write for xxx, then this equation will look like this. Lambda I divided by 2. This is index. J, lambda G minus I divided by 2, raising the power total length of the lattice is equal to the product K from 1, and here I have lambda J, lambda K, I squared of minus 1. This is good equations actually because Hans Bethe wrote them. This is periodic boundary conditions. Remember when I wrote originally in 1932, Hans Bethe imposed periodic boundary conditions. That's exactly periodic boundary conditions. So it's kind of nice. I can compare this wave function B with this expression which I had summation with respect to Q to permutation. All eigenvalues. I mean, I also can extract energy from here. I can, mu dependence doesn't go into here. Mu dependence only into here. So if I take logarithmic derivative of this thing, I will get energies, and energies also will fit into the expression which Hans Bethe obtained. So I have feeling that this thing, B, is actually proportional to the eigenfunction which I wrote in the very beginning, summation with respect to permutation. Well, to be on the safe side, I have explicit expression for L operators, so I can take it, like multiply all of them and calculate this BBB, and it will fit. This is exactly the wave function which Hans Bethe wrote. It's lengthy calculation, so I'm skipping, but there is straightforward brute force proof that this BBB reproduces exactly the wave function which I wrote in the beginning. So this is nice. We managed to factorize the wave function. The wave function which originally was written in the sum of n factorial terms now is the product of n factors m pure, and they commute with one another, and we have a tensor network for this. And then this kind of related, these spin chains, they are not pure mathematical objects. By now, there are experiments done in optical lattices where people try to build these spin chains. People shine lasers to one another, get a standing electromagnetic wave, put cold neutral atoms, which got a dipole moment because of the interaction with the wave. And then the dipole moment interact back So standing electromagnetic wave. And the atoms, because of the interaction with the wave, got some dipole moment, which interact back with this wave. So cold atoms stay in the maxima of this standing electromagnetic wave called optical lattice. And this can be one-dimensional, two-dimensional, three-dimensional. And actually, people can build this XXX and XXZ in the lab. And the people who do this, Emanuel Bloch in Europe, Jörg Smithmeyer, and even in Stony Brook, Dominic Schnebel, we have our own experimentalists in Stony Brook who is also doing this. It's called simulation. Part of the title of the workshop. Simulation. Of course, they can build it, but this is finite lattice, and also no periodic boundary conditions either. So we actually needed to modify all of this to the open boundary conditions, not to periodic boundary conditions. Before we do that, before we modify tensor networks to open boundary conditions, we need some extra piece of algebra from this in order to move to open boundary condition. So the extra piece of algebra out of these ABCD operators, there is something which is called quantum determinant and antipode, and we'll need that. So if I have normal matrix, just with complex entries matrix, if I want to invert it, I mean, this is matrix 2 by 2. Then this Kramer formula I can write in the compact way, which is sigma y, then here matrix transposed. This same matrix transposed, sigma y divided by the determinant of this matrix. This is usual Kramer formula, which is known for many years. It turns out that something like this can be applied to T. I want to invert my monadry matrix. Its entries quantum operator, so it's not as easy, but something like this works, and inverse T called antipode. So the main idea out of this, I mean, our matrix depends on the spectral parameter, lambda mu. If the difference of these two spectral parameters in the XXX case is I for the XXX guys, then our matrix become highly degenerated. Our matrix turn into swap gate permutation minus identity, which is 4 by 4 matrix, look like this, with this 1, 1, minus 1, minus 1, the rest is 0. This is one-dimensional projector. So determinant, this is really the genus. So commutation relations become very, very, very special. With the difference between lambda and mu is equal to y, then everything becomes very, very special. So this helps us to define quantum determinant. Quantum determinant is the center of the algebra, some operator which commute with A, B, C, D, and which each and every quantum operator which I saw in this construction. So this quantum determinant has some formula. Quantum determinant T of lambda, my A operator for the XXX case. D minus B C. So what's so remarkable, this thing, quantum determinant, commute with all the operators which I saw. I mean, if I take any matrix elements of T, A, B, C, D, it will be 0. It's the center of the algebra. Okay, this is nice. And then I can use this in order to invert this using this formula. So T inverse look like this. The same sigma y. The T here I have to transpose, but I have to shift the spectral parameter. This is transposition, lambda plus I, and then I divide by my quantum determinant. And quantum of lambda plus I divided by 2. It's called antipode. It's important for, I mean, Yang-Baxter algebra, and also in order to rewrite this tensor network for open boundary conditions. So let me erase all of this. Now we change boundary condition from periodic to open boundary condition. So I'll change even notations a little bit, because there's different community of people who do open boundary condition. They use, well, let me write it down. It's called reflection algebra, the algebra which I'm about to explain, called reflection algebra. There are some people who invented this, and then I'll write these names momentarily. So there's two people who invented, who reformulated. Yeah, anyway, I'll be using the algebra which was designed by two people. First,
Question.
yeah,
Sorry, I got confused by one thing. So you're going to do open boundary conditions
Yeah.
now. But is that was done some time ago?
it's history. Yes, that is yes in first approximation. But then I can give details. There is a French book, Michel Godin from Saclay. He wrote this book. It's in French and in Russian, but with coordinate Bethe Ansatz. The first formula for the eigenfunction, which I refer to Hans Bethe, it's called coordinate Bethe Ansatz. So Michel Godin wrote the coordinate Bethe Ansatz wavefunction for open boundary condition in that book. Okay, but then this is not good for us because it's even more terms. It's like n factorial multiplied by 2 raised to the power n. So he solved it, but computational efficiency went down. It's even more complex. So we don't want that. We want algebraic Bethe Ansatz, which is tensor network. And tensor network was reformulated by 2 other people. And then those are foreign people with foreign Russian names, so I have to transliterate the names on the blackboard. Eugene Sklein, he's in Leeds right now in England, and also Cherednik. Cherednik, he's in North Carolina right now in Raleigh-Durham. So they invented something which they call a reflection algebra. Basically, did I answer your question?
I don't know. So I wanted to understand the connection with matrix product states and whether...
There will be new tensor network. You want me to draw the tensor network? So the tensor network for open boundary condition will be different. I will have, like, instead of a line, I will have a loop. But before drawing this, I was going to feed you with some more algebra. So, yeah. So Sklein and Cherednik use different notations. First of all, Yang-Baxter equation is still important for open boundary condition. The R matrix for x, x, z cases, it's exactly the same, but they use u instead of lambda, so spectral parameter will be u, and there is some more, couple of other changes in notation. So spectral parameter, this was lambda. It's still 4x4 R matrix, and still the entries. So this is A, B, C, A. And those are still trigonometric hyperbolic functions, just a little bit of change of notation. Sine hyperbolic, u plus eta. Those are elements of my, this was my f and g. And b is sine hyperbolic of u, and c is sine hyperbolic of eta, which is anisotropy. Remember, anisotropy was in the Hamiltonian. So these R matrices still satisfy Yang-Baxter equation. Yang-Baxter equation, like roughly speaking, R cube is equal to R cube, but I need like 3 spaces. But I wrote this in some precise way, so let's leave it rough for now. But in order to formulate this open boundary condition, what the picture is, this is my lattice, and in that there's some wall. And the wave, spin wave, reflects from the wall and go back, then reflects from this wall. There is scattering matrix of the wave from the wall. It's a new element that was not present before, and it's denoted by K. In our case, it will be matrix 2 by 2. Depends on the spectral parameter. And there's some equations, the reflection algebra, which they have to satisfy. And this is like addition to Yang-Baxter, so I just want to write it down and then also write the picture. So this Yang-Baxter equation, reflection algebra, generalization of Yang-Baxter. This is the difference between spectral parameter which we saw before. This is reflection from the left wall. Then this, well, anyway, u1 plus u2. So this was the difference, this is the sum. And here reflection from the other wall. And this is like one auxiliary space, another auxiliary space, u2. And this is supposed to be equal to k minus u2 r12 k1 minus of u1 r1 2. It's called a reflection algebra. And then one of our co-authors managed to write a picture for this. Yang-Baxter equation is cubic relation. Remember, I wrote it like this. So just the meaning of this, that one line moved through the intersection of two others. I just lift this 3 through the intersection. That was Yang-Baxter. In here, the picture for this new equation is like this. So K is the fat square with a fat error. So the picture is like this. For this, I'm trying to draw this equation. So this I'm supposed to think about this as a spin wave with a spectral parameter u1, which was lambda in the previous part, and this is u2, and this is u2, and this is u1 minus u1, this is u2 minus u2, and this is u2 minus u2, minus u2 in here, u1 minus u1. So the meaning of this, so this is my K-matrix. This intersection is R matrix, R matrix, R matrix, and this basically means some equation which entangle reflection from the wall matrix, describing reflection of the wave from the wall with the scattering matrix between themselves. So this is additional extra piece of equation which are necessary for model with open boundary condition to be solvable.
K and R generate the algebra?
Oh, no. K, at first I solved the Yang-Baxter equation and fixed equation for something which was known before, x, xz. Then I write this equation, try to find some solution. And some solution which has physical meaning and corresponds to nice Hamiltonian. And the case which I will have in mind in my example.
What are the generators of the algebra? Or what is the
For XXX, everything based on SU2 algebra. Originally, everything was based on SU2 algebra. There are more hidden symmetries of this, but probably for the infinite lattice side, the algebra get elevated to infinite dimensional representation of Yangian, but I'm not using this in here. People call this Yang-Baxter algebra, algebra of this ABCD, the one which I wrote. Traditionally in the literature, they call it Yang-Baxter algebra. So K, our matrix I already have in mind. K, the simplest K, which is used, in the papers by Sklerin and Cherednik, is K dependent on spectral parameter, some extra parameter. And the simplest K, this is diagonal matrix 2 by 2. So sine hyperbolic. Here I have a spectral parameter plus some anisotropy, and here minus. Same thing. U minus psi. So what I'm saying that this K solve this equation. This is a solution, like Sklerin and Cherednik solve it. So just not ad hoc thing. I have to check it, and somebody else already checked this. So from now on, I can try to reproduce all these nice algebraic structures which I have with periodic boundary condition. I try to, construct them here. And then what comes out, remember I have this commuting family of infinite many conservation laws, and I have a generating function of conservation laws which was A plus D, right? So instead of A plus D, in open boundary condition, I have something else, which is trace in the auxiliary space of this K plus. I have two walls, reflection from this is K plus reflection from this wall and K minus reflection from this wall. So I have K plus minus, it's time running out?
Yeah.
Okay, so the tensor network. Anyway, so Hamiltonian, XXX Hamiltonian look like this. Sigma, m plus 1, plus I have some local magnetic field in the first lattice side, plus local magnetic field in the last lattice side. That's additional extra thing. And the tensor network look like this right now. So I have to erase it. Just I draw tensor network and then this will be it. Because there was questions about it. So tensor network looks like this. Remember, I have this, my L operator, and one spectral parameter is the same spectral parameter. This is auxiliary space. This is some specific vector, then I continue like this. And this is as many as the length of the lattice. V1 multiplication in the auxiliary space. Then this K-matrix, and then I go backwards. The V1 in the same lattice site, in the same quantum space, and then this is V1 in the same, like here, and then go back to here, still V1, and then another matrix element. I have to repeat this for each and every V's. So it's kind of, this tensor network is kind of doubled comparing to periodic with K inserted in the middle. Anyway, so since I'm running out of time, we have this tensor network for open boundary condition. Also, we can calculate expectations. We can calculate correlation functions, and the correlation functions for open boundary condition, the finite lattice, there's no other way to calculate except of our tensor network, so we just calculate them numerically using some numerical ideas which were published by Ignacio and Frank and Murk in the previous publication. And then this is helpful for these simulations which is done in optical lattices. And so we try to relate tensor network with simulation. That's a subject of this workshop and the end of my lecture.
Okay. Time for maybe a few quick questions.
Yeah.
From this reflection algebra, do you also get the new set of equations for the spectral parameters?
Yes. Thank you for asking this question. You can ask me just present all the transparencies which you didn't have a chance to. So x minus mp. This was the left-hand side for periodic boundary condition. Now I put 2 mp because go to the left, go to the right. Then k11 of u. And in the right-hand side, I have this product of S matrices. Remember, minus I theta was lambda j minus lambda k. But here I also add, subtract theta of lambda j multiplication with respect to k plus lambda k. So double length here, reflection from the wall, and here this is old factor, like in periodic boundary condition. And here this is like the wave go backwards. So instead of the difference, you get the sum. And these equations in the Godin, Sklanin, Cherednik, all of this, but they do change.
Okay, there are no more questions. Let's do the lecture again. Maybe we take a 20-minute coffee break or start again at